Welcome to the second part of the lecture. What we saw up to now told us that the interaction between the stellar radiation and protoplanetary disks creates a temperature gradient inside the disk, which in turn creates a compositional gradient, with the more refractory elements condensing closer to the star and more volatile elements increasingly adding up to the condensed planetary materials. And we saw that this is reflected into the compositional gradient that we see in the population of minor bodies in the solar system, among the asteroids and the comets, both comparing the two populations. So asteroids as rocky material closer to the star and comets icy material coming from the outer region of the solar system, but also within the two populations. Asteroids present a gradient with more volatile material appearing in asteroids that are further away from the sun. And similarly, the comets possess different abundance of elements of different volatility, which suggests their formation across a wide extent of time and space in the disk. The situation up to now would seem reasonably clear and simple. So we have already a compositional gradients, and materials forming at different distances from the star will have a different composition. And this seems to be supported also by extrasolar data. However, up to now, we have not included the presence of planets in the pictures. What happens when we move from the formation of the smaller bodies like the planetesimal to the formation of planetary bodies like we see today in the solar system and that we observe around other stars with the exoplanets? What happens is that once a few bodies start reaching the size, a size comprised between that of the Moon and Mars, so between 1% and 10% of that of the Earth, they start to gravitationally accrete all the smaller bodies, growing faster than the other bodies. And these planetary embryos, that becomes oligarchs. So the few bodies that grows, the name literally means the few bodies that rule. As you can see in the simulation on the bottom right, where you have the oligarchs, the planetary embryos in red, that interact with a population of smaller bodies of different colors, which represented the different region from which the planetesimal originated. And you see that the number of smaller bodies decrease, and also number of oligarchs, until we end up in this simulation with 3 terrestrial planets mimicking Venus, the Earth, and Mars, more or less. As you can see from this simulation, there is an interaction between these planetary embryos while they grow into oligarchs and then terrestrial planets, and the population of small bodies cause a complete remixing on the planetary material. In this size range of the stage of planetary growth, impacts even between large bodies, like between two oligarchs, the red bodies in the simulation on the bottom right, tend to be always accretionally. So they can be approximated as completely inelastic impacts, where the final mass of the remaining bodies is, to good approximation, the sum of the mass of the two impacting bodies. We can see this process from another point of view in the simulation here on the left, where you can see the diffusion of volatile elements represented in blue by the by both bodies that possess a larger fraction of water in their composition. And as you can see, bodies, the blue bodies, the water-rich, volatile-rich bodies, tend to diffuse into the inner region of the planetary system. The planets that are forming have a color that shifts from red to green and blue across the simulation, because they are gathering more and more water from the bodies that formed into the outer part of the asteroid belt. Notice that in the previous simulation and in this simulation, Jupiter is already present and is the one that is exciting the asteroid belt and causing the bodies to go on orbit and intersect those of the terrestrial planets. So this fountain here, the excitation wave, is due to the presence of Jupiter. This process is stochastic in nature, and an example of the effect of this stochasticity of the process is shown in the right plot, where you can see, as these cake diagrams, the composition of the planets that are formed in different simulations in terms of material coming from different distances from the sun. Already you can see that the process is random and stochastic because the number of planets is not constant, and is not constant also the mass of the planets at the end of the simulation, nor the distance. But you can also see that the final planets have very different composition from one case to the other. And they all include material, a mix of material that comes from the different region. So even if the beginning of the planetary formation process from the protoplanetary disk to the formation of the first generation of planetary bodies create a compositional gradient, the planetary formation process, while it continues in order to form the terrestrial planets, has inbuilt an effect of remixing of the planetary material, which means that we don't find necessarily planets composed by material that was available in situ, but they can contain material that was not original of their formation region, but came from other region because of dynamical encounters, scattering, and accretion. Now, I mentioned that in the simulation, Jupiter was already present before the terrestrial planets. Why this? Because if we look at the giant planets in the solar system, the bulk of the mass of Jupiter and Saturn, as well as a large fraction of the mass of Uranus and Neptune, are composed of hydrogen and helium. Hydrogen and helium, if you remember, are not elements that condense and are available in large amounts in meteorites, and they also don't condense in large amounts as pure hydrogen and helium among the volatiles. Part of them is contained into, for example, ammonia and water, but because the abundance of hydrogen and helium is much higher than that of the other elements, the vast majority of these elements remain always in gas form in disk. So, the giant planets should form before the dispersal of the disk, because otherwise, since hydrogen and helium don't condense in the condition of protoplanetary disk, there are no sources of hydrogen and helium available for the planets to accrete them after the dissipation of the disk. Now, giant planets, according to the data we have for the giant planets for the solar system, are generally thought to form initially in a similar way as the terrestrial planets, like a seed that grows, creating the smaller material around until it reaches a mass of a few Earth masses, at which point it starts creating a gas atmosphere from the gas of the disk. The process of accretion of the solid core and of the atmosphere continue at different rates until the gas atmosphere is more or less equal in mass as the solid core. At this point, a process of instability is triggered. The gas is not supported anymore by the thermal pressure and starts being rapidly accreted by the core of the giant planet. The fact that the gas collapses on the core means that more space is available for other gas to diffuse and be accreted by the planet, and the process continues rapidly as a cascade until the planet, in a few 10 to the 5 years, reaches its final mass, which in the case of Jupiter means that over this time scale, the planet jumps from 30 Earth masses to more than 300 Earth masses, so grows a factor of 10. Now, up to now, we have talked about planetary formation as a local process, but is it a local process? If we look at the distribution of the exoplanets we know in terms of orbital distances or orbital periods, which is equivalent, we see that 75% of the exoplanets known today orbit at orbital distance that is associated to orbital periods of 100 days or less. By comparison, the orbital period of Mercury is around 90 days. And given that most of the stars are similar to the Sun, this means that the vast majority of the exoplanets we know today, both super-Earth and giant planets, orbit closer to the star than Mercury in the solar system. Given that there is not enough mass in these regions to form the cause of giant planets, even if we assume 100% efficiency, unless we are missing something in the details of the planetary formation process that we think we know, this suggests that these planets migrate from other regions. And we get a confirmation of this if we look at the densities of the planets. Here you have, again, orbital period and the planetary mass in jovian masses. Here you have the giant planets. Here you have sub-Neptunes to super-Earth planets, with a few planets with mass comparable to that of the Earth. And as you can see, in this color scale of the density, where 1 is the density of water ice, and 8, the red, is the density of the iron-nickel league that compose the core of terrestrial planets, we don't have any compositional gradient at all. We have a mixture of planets with low density, with planets with density compatible with metals, and everything in between. For comparison, the density of the Earth and of the terrestrial planets in the solar system is around 5. So it's between the transition from green to yellow. Again, this lack of any compositional gradient suggests that planets formed at different distances from the star were brought there by migration. Now, there are 2 mechanisms through which a planet can migrate. The first one is by its interaction with the gas in the disk. There is an exchange of angular momentum, and the planet can be brought closer to the star by losing angular momentum that is gained by the gas. However, there is another mechanism, and this other mechanism is the role of this other mechanism is actually supported again by the extrasolar data. Because if we look this time at the eccentricity of the orbits of the exoplanets we know, again as a function of the orbital period, for example, we have that 50% of non-exoplanets, everything in the red area, has an eccentricity greater than 0.1. By comparison, the eccentricity of basically all the planets in the solar system, except for Mercury, are an order of magnitude smaller. Now, we know that eccentricity is generated by interaction with large perturbers or planet-planet scattering events, as we saw in the simulation for the formation of the terrestrial planets. The interaction between the embryos, the oligarchs, and the small bodies caused the eccentricity of the small bodies to increase. And if we try instead, if we put eccentricity into the global picture of dynamical excitation, and we compute the dynamical excitation of a planetary system that we know, we see that another important fact. Basically, not only we have a large fraction of planets that have a higher eccentricity, higher than the planets in the solar system, but we also have a large fraction of planetary system as a whole that have a higher dynamical excitation than the solar system. In this plot, you can see a metric of the dynamical excitation that you can see reported here, which is a function of the mass, the major axis, the eccentricity, and the relative inclination of the planets in a planetary system, as a function of the number of planets in the system. This plot tells us 2 things. First, a large fraction of the best characterized as exoplanetary system that we know today have excitation higher than that of the solar system. The solar system is not alone in being among the planetary system with low global dynamical excitation, and there are systems with lower dynamical excitation than the solar system, but a large fraction of the planetary system have higher values of the dynamical excitation. The other thing that we might notice is that there is a decreasing trend in dynamical excitation among, as a function of the number of planets. So systems with fewer planets tend, on average, to be more dynamically excited than systems with a larger number of planets. Now, the statistical system with a larger number of planets, it is still limited, so it's something that will need to be confirmed by future studies when we'll have a better statistic. However, the trend between a system of 2, 3, up to 4 and 5 planets is reasonably robust and shows this decreasing trend. This might suggest that some of the most excited systems with a small number of planets in reality were born with a higher number of planets and lost some of them due to global scale dynamical instabilities, for example. Remember that dynamical excitation is produced when we have large perturbation in the system, or that can be also caused by global instabilities, chaotic dynamics, planet-planet scattering events. While generally, smaller dynamical excitation values are associated to more regular evolution. So generally, we tend to say that a large fraction of planetary systems tend to have undergone more violent dynamical histories than the solar system, which suggests that there is a second pathway, which is not uncommon among planetary systems, that can cause planets to migrate because chaotic evolution, planet-planet scattering, and generally global scale instability. And it is interesting that this kind of processes were proposed also for the solar system, notwithstanding the fact that the solar system was used in the previous plot as the division line between highly excited and less excited planetary system. There are a number of scenarios that have been proposed for the solar system. Some proposing global dynamical instabilities, other combining large-scale migration with dynamical instabilities. And some of them even proposing the presence of additional giant planets originating in the solar system and the loss of some of them. This pathway of evolution of the solar system appear even more plausible now that we put them in the context of the dynamical evolution and excitation of exoplanetary system. So it is for this reason that the solar system can be used as a division line between systems that more likely had a variant dynamical history and systems that more likely had a stable and irregular dynamical history. Because for the solar system, we have both classes of scenarios, all of them succeeding in explaining some of the characteristics of the solar system and having more difficulty in explaining others. However, we talked about the fact that the final position of giant planets is not necessarily representative of where they formed, and we spoke about the formation of the giant planets and the terrestrial planets in the solar system, which seems to indicate that planets form in the first few tenths of a year from a planetary system. However, if we look at other circumstellar disks, this vision can be challenged. Now, thanks to the Atacama Large Millimeter and Submillimeter Array of radio telescopes in the South American desert of Atacama in Chile, we've been able in the past 6 years to get an increasingly higher resolution in the observation of protoplanetary disk. By comparison, here you have a vintage image from mid-90s of the protoplanetary disk seen with Hubble. And here you have images of protoplanetary disk seen 2 years ago by the large program D-Sharp of ARM. When giant planets form, they tend to clear the surrounding region by both solid material, dust and planetesimals, and by gas, because of their accretion and the larger gravity that perturb the surrounding region. And this prediction of this gap in the disk of gas and dust surrounding the star are actually confirmed by observation of ALMA, where we see widespread presence of such features as rings and gaps. In some cases, it is possible that some of these features are not actually related to planets, but more likely to the evolution of the disk. However, in other cases, some, like for example, the case of HD 163296 at the bottom right disk in this mosaic, there are different lines of indication that suggest that these rings are actually caused by the presence of giant planets embedded in disk. However, if you look at the bottom of each tile of the mosaic, you will see there is a small white bar that represents the scale of 10 astronomical units in that specific image. And as you can see, in most of the disk, the features associated to the presence of possible giant planets are much farther away than what we see in the solar system. They go from several tens to hundreds of astronomical units from the star. So the giant planet formation region in disk that is suggested by these images is much different from the one that we would have expected from the structure of the solar system, and suggests that large-scale migration could be a common stage in the life of planetary system, given also the widespread presence of planets at very close distance from the stars revealed by the exoplanets. And what happens when we put giant planets in disk so far away from the star? What happens is that, as we expected, the planets clear a gap also in the planetesimal distribution because of the dynamical perturbation. But because the gravity of the planets with respect to the gravity of the star becomes much more important in dominating this region, the global effect is that the population of planetesimal gets very dynamically excited and creates a population of exocomets with very high inclinations and very high eccentricities, as you can see in the animation of the excitation process of the disk of HT 163296, the one on the bottom right in the previous slide. This is a simulation with the mass closer to the most up-to-date estimates of the mass of the three giant planets. As you can see, a huge population of exocomets with very, very high eccentricities produced. This is important from the point of view of the composition of the planetary bodies, because this means that these planetesimal have very stretched orbit that can cross wide region of the planetary system, and they can collide and be accreted by body forming very far away from when these planetesimal were formed. Moreover, some of these planetesimal can reach such high eccentricity that they can penetrate the inner regions of the protoplanetary disk, where the density of the gas is such that can start circularizing their orbits closer to the pericenter. And this is the cause of this fountain, this cascade of planetesimal toward the inner region. Now, the inner edge of this disk is a 10 astronomical unit, and this means that the presence of giant planets at 50 to 150 astronomical units from the star can excite planetesimal and inject cometary objects rich in ultra-volatile elements into the innermost region of the protoplanetary disk, where we would expect analogs of the planets of the solar system to form. So again, the presence of one or more large perturbers at large distances can also have implication for bodies that are forming into the inner regions. And the fact that planets can form at such large distances means that also in the case of the solar system, we cannot exclude automatically that the giant planets of the solar system forms a few tens of astronomical units from where we see them now. Here you can see an example of a simulation studying the formation of the 4 giant planets of the solar system, starting with their seed in the region comprised between 15 and 30 astronomical units, so beyond the orbit of Saturn and more or less around the orbit of Uranus and Neptune. The seed of the planets start at this distance, but the planets migrate to reach position closer to the final position. And as you can see, while crossing to this, because of the large mass, planetesimals can be dynamically excited and remixed with a fraction of planetesimal that were formed at very large distances from the star. Here, there are also bodies that formed at 15 to 20 astronomical units, and they can be injected into the asteroid belt. While this would seem extreme, giant planets forming so far away and migrating to the final position, creating such a huge remixing of the planetesimals and therefore the planetary material, there are a number of hints that suggest that this could actually happen in the solar system. For example, the fact that Vesta and Ceres, 2 of the asteroids in the asteroid belt and the target of the NASA mission Dawn, both showed the presence of volatile material that was not local to the region where they, the orbital region where they are now and where they plausibly formed. and suggest that they have created the material that was more rich in volatiles than the local material for which they were forming, while the protoplanetary disk was still present in the first few million years of the life of the solar system, which exclude a role of the terrestrial planets and the remixing they cause as the source of the accretion of this material. Now, we approach the end of this lecture, and let's see if we can if we can show that we can use composition to tell something about the specific history of planetary bodies, in the specific case, giant planets. It has been observed that giant planets sharing a similar, the same mass among exoplanetary population can have very different densities or abundance of heavy elements, where with heavy elements we indicate everything that is not hydrogen and helium. The presence of different densities has been interpreted as an indication that these giant planets, during their formation process, have created different amounts of solid material that was suggested to be linked to their formation in a different region for the stars. Why? Because it has been shown that there is a direct correlation between the extent of migration, or equivalently, the distance from the star at which a planet starts its formation process, and the amount of material that it can capture in migration. In all this simulation, the planet stops its migration at 0.4 astronomical unit, so it becomes an old Jupiter, or more properly a warm Jupiter, because its temperature would be of the order of 1000 Kelvin. And you can see that keeping fixed the final position of the planet, we have different starting points, therefore different extent of migration. And the farther away the planets form, the larger is its migration, the greater is the amount of heavy elements that are captured, here expressed in units of terrestrial masses. That would suggest that just by looking at the density and therefore the mass and radius of a giant planet, we could constrain its formation region. However, there is a complication. It's the fact that the amount of material that is captured, and therefore the density of a planet, depend also on the time scale on which the giant planet migrate. As you can see here, a slightly slower or faster migration time scale, a slightly faster or slower migration time scale can cause the giant planets to mimic the effect of informing farther away or closer to the star, introducing a degeneracy in this picture. We can do something better if we add composition in terms of abundance of different elements in the picture. This was proposed about 10 years ago by using by identifying the C/O ratio, carbon to oxygen ratio of planets as a measure, as a tracer of the formation region and their migration. This is based on a very simple and powerful idea, which is the fact that because oxygen condenses closer to the star than the bulk of carbon, because as we saw, a good fraction of oxygen is condensed there with the rocks, and then water brings more oxygen, and so CO2, while carbon starts to get accreted with CO2 first and CO after, at larger distances. The C/O ratio of the gas, where the oxygen is subtracted and goes in solids quicker than the carbon, will grow linearly with distance, while the C/O ratio of solids will decrease and remain subsolar for most of the extension of the disk, becoming insolar when all the carbon and oxygen are condensed into solids. However, there are two limitations to this, the application of this picture. One has been highlighted by simulations studying the C/O ratio produced by different formation and migration scenario. Here, this migration is the early migration due to interaction with the disk, and this free migration can be one of the mechanisms associated to the dynamical instabilities produced in the dynamical excitation of the planetary system that we saw. So like planet-planet scattering, chaotic dynamic, etc. And as you can see, it is possible for different formation and migration scenario to produce similar or even the same C over O ratio of the planet, again introducing a degeneracy. The other problem is that the distribution of carbon and oxygen is continuously changing while we refine our understanding of the chemistry of meteorites, comets, and generally astrophysical environments that are related to planetary formation. And if we look at the most up-to-date picture, the simple to understand the C over O pattern identified by Oberg and collaborators in reality gets a bit more complex to interpret. First, because due to the role of water, rocks, and organics, as highlighted by the cometary data, for example, of Comet 67P and the Rosetta mission, about 60 to 70% of oxygen and carbon can be already trapped in solids in the first few AU of the disk, which means that after the first few AU, the C over ratio of solid material can be already very, very close to that of the star and can remain very close, indistinguishably close to the star for most of the extension of the disk. Similarly, the C over ratio of the gas does not show a monotonic trend, but in reality oscillates around the value of 1. This different trend makes interpreting the C over ratio a bit more difficult. This difficulty, however, can be bypassed if we expand the suite of elements that we can use to trace the formation and migration history of planets. An example that I will use to illustrate you how we can do this, coming from a recent work that we did in the framework of the Ariel mission, uses nitrogen and sulfur as 2 additional elements. Nitrogen, because it is characterized by a higher volatility than carbon and oxygen. As I showed you before, in the first part, a part of nitrogen is trapped into solids by ammonia, but the vast majority of nitrogen remain as a gas in the disk and condense only very far away from the disk as N2. Sulfur, on the other hand, is incorporated into solids very early in the disk, and the bulk of sulfur is in refractory form in rocks already from the first few U. So it has a lower volatility than carbon and oxygen. If we put these tracers into our simulation of the interaction of a migrating and accreting giant planets in a planetesimal disk, and we trace the accretion of gas and planetesimal by the giant planets, and we decompose the material that is accreted across the different region, and we compute the contribution of the 4 elements of the gas and solids to the 4 elements, we see that actually the C over ratio for planets forming at tens to hundreds of astronomical units, each symbol is the starting point of the giant planets in this set of simulation, you can see that the C over O ratio provides very limited information of the distance at which the giant planet formed from the star. The two curves that you can find here in green and violet are basically flat. The purple indicates bodies that accrete both gas and solids, and which a significant fraction of the metallicity, the abundance of LEV elements, is contributed by solids. The green curve instead is for planets that accrete only gas and derive only the metallicity, therefore the fraction of heavy elements, from the gas. We can distinguish, thanks to the C over O ratio, one regime from the other, but we cannot tell where the planet formed. We can add more color to the picture, to go back to the analogy with which we started this lecture, if we consider the C over N, carbon over nitrogen, and N over O, nitrogen over oxygen ratios. As you can see, the two curves are not flat. They show monotonic trends, increasing or decreasing depending on whether you are dominated by the accretion of gas or with a significant contribution of solids, and whether you are considering C over N or N over O. But you can see that the values deviate from the stellar values the more, the farther away the planet starts its formation from the star. in a monotonic way. In the case of the C over N ratio, because inside, rocks traps very little carbon and basically even less nitrogen, carbon and nitrogen are all in gas form in the innermost regions of the disk. So planets that form start their formation and migration closer to the star might capture all the carbon and nitrogen mainly through the gas, bringing the C over N ratio to be very close to the stellar value, and therefore not being able to deconvolve whether our planet created only gas or a significant fraction of solids. This doesn't happen with the N over O ratio, however, because, as we saw, a certain fraction of oxygen is always trapped into rocks. Might be 50 or might be 20%, depending on how close to the star the rocks formed. But while nitrogen is basically all in gas form close to the star, oxygen is always subsolar in the gas, and a fraction is trapped into the rocks, as the meteorites tell us. So the N over O ratio of giant planets creating a significant fraction of solids and planets dominated only by the accretion of gas will never converge to the same value. And again, you have monotonic trends deviating from the stellar values the farther away the giant planet formed, so the more it migrated. I spoke about 4 elements I took only at the beginning, and I showed plots only for 3. What happens when we consider also sulfur? Basically, sulfur, as I said, has a lower volatility than carbon and oxygen, and therefore also nitrogen, while nitrogen has a higher volatility. As a result, for most of the extension of the disk, nitrogen can be considered as a tracer only of the gas, while sulfur can be considered as a tracer of the solids. If we look at the curve of the S over N ratio and the curve of the accretion of solids, we see that they share the same shape. So basically, the S over N ratio traces the accretion of solid materials, so planetesimal, by the giant planet. The violet curve, instead, show the total metallicity of a giant planet, that is a mixture, the combination of the contribution of heavy elements by solids, planetesimals, and gas. For very high metallicity, the main source are the planetesimals, as you can see for very large migration, and the 2 curves basically overlap. So if we have the estimation of the sulfur over nitrogen ratio and we compare it with the metallicity that we can estimate from the density or the mass radius relationship of a giant planet, and the 2 match, we know and we have a confirmation that the giant planet formed far away from the star and accreted most of these heavy elements through solids. However, you can see that in the innermost region, because the contribution, the mass accreted in terms of solids decreases, the contribution of heavy elements of the gas becomes comparable to that of solids. In this case, the metallicity derived through the mass radius relationship will be higher than that derived through the sulfur over nitrogen ratio. Therefore, the use of this elemental ratio as an additional color in our picture allows to further discriminate between the 2 regimes, whether the metallicity is mostly dominated by the accretion of solids or is contributed both by gas and solids. With this, I conclude. I'm pretty sure that you will have a number of things that have been unclear because we had to pack a lot of different subjects and information from different disciplines into a short lesson of 1 hour. So if you have any question, there will be a live question time where you can ask everything that you are unclear. If you want to send me question ahead of the live question time so that you are sure that you get your response by the time of the live question time, feel free to do so. Here you have my email address, and see you in a couple of days.